So this is going to be a line integral of a helix, basically. So in this case, our field in XYZ plane is so it's a vector field, right? So we have vector notation, and we're given z, x, and y as our components. I said x and I wrote y. So z, x, and y. And remember, these are still in normal I, j, k. So these are still in normal x, y, z. The x component is z, the j component is x, and the k component is y. Like, we just have to keep that in our minds, that we're still operating in our normal vector respectiveness. The function just has a different value in those different directions. It can be a little tricky to get your head around. This is one of the harder things in multivariable calculus for sure. So for this one, the curve is a helix. Now let's think about that for a second. There is a defined function in here, but I just want to talk about it for a second. So the curve is a helix. What does that mean? So let's think about a helix. So helix is, if you're looking top down, right? So then if top down, then this is x and y. So a helix is just a circle, right? Because if you're looking at it from the top down, I guess I'll do it this perspective, it'll make more sense for you. So this is just what it is in the top down view, it's just a circle, because it just goes like this. But then if you lay it down, it's going to be going up, right? Because the helix, it's a spiral. So now if we look at the side view, let's say this is x and this is z. So in this case, it's going to go up and around, and around, and around, and around, right? So it's a circle that goes up by x. So basically, we're kind of expecting that the x and y components might be something like this, right? Because that's usually what we expect for a circle. And then z, we'll just say that the rate of change here is just z. And then we can do I hat, j hat, and k hat. So I'm expecting it to look something like this. Now let's see what the book has defined it as. Oh boy, okay, they're using polar form for this one, which is phenomenal. So in this case, they're saying that they want it to be where your vector with respect to t is equal to cosine t, sine t, 3t. Now, that actually still is pretty close. The only thing is they're defining a z for us that I just didn't have the information just going from a general form. But x squared y squared does make sense with cosine sine. So that tracks. That actually works with our initial intuitive understanding of this problem, hopefully. And then all we know now is that z is 3 in my example. Okay. So now that we kind of have an understanding of what we're doing here, I'm going to rewrite this over here so we can clear out our space. So cosine of t, sine of t, and 3t. Now I'm sure there's pretty obviously something you've noticed, that we have x's and t's and y's and z's, and what the heck's going on? So easy deal with, this is really easy to deal with at this point. Recall, this is an x, and this is a y, and this is a z, right? We were just talking about that. So what happens if we just plug those in here? Because we have f and we want to plug r in. So let's plug r in. So now we're going to say f of r of t, the parameterized position vector plugged into our vector field, and then we're literally just going to plug these in. Now this is where people make mistakes. You want to plug in the thing it says with that component of your position vector as it's been parameterized. So we have a z here in our first component. The z is 3t. So we have 3t. And then our next component is our x, so we've got cosine of t. And our final component is our y, sine of t. Oops, that should be a little bit more angular. There we go. Okay, so now we've got our parameterized position vector in our vector field. Now, in order to evaluate this, we need to find our prime of t. Because what we're going for is an integral over a curve of f r of t comes from the other one we were looking at just a moment ago of f of r dot ds. Those are the same integral, right? And so this is a translation into a new integral form, and then we just need to find all of our pieces. So I like to think of this as a checklist of puzzle pieces I need to find. And my checklist as such, I need to find first r of t, right? We need r of t first. And then we're going to plug r of t into f of r of t. And then we're going to find r prime of t. And then we're going to plug it all in and solve integral. So we've done r of t. That was thankfully given to us in this case. We've plugged r of t into f of t. So now we need to find r prime of t. So r prime of t is just going to be the derivative of our parameterized position function. So the derivative here with respect to t is just going to be negative sine of t. And the derivative of here is just going to be cosine of t. And the derivative here is 3. Alright, so that's r prime of t. Good. Now we have r prime of t. Now we can plug everything in and solve. So I'm going to erase our checklist because we have everything we need. So these integrals, it's really helpful if you write a checklist every time so you know what you need, you know what to solve for, and you can plug in all of your puzzle pieces and make your life easier. In this case, since we're doing, the only other thing we needed that we didn't write down on our checklist was bounds. So remember we're doing this helix. So it's defined as a circle, which generally speaking, if we want to integrate over circles, we need to integrate from 0 to 2 pi. So in this case, that's what we'll do. So our curve is the helix from 0 to 2 pi. I don't know if it said that. It did, yeah. Okay, so the figure it drew, it showed from 0 to 2 pi as well. So you would usually get that information from your question. Okay, so now we're going to do the dot product of these two vectors, and then we'll do the integral. So we have 3t, comma, cosine of t, comma, sine t, dot, right? Our notation is super important here. It's easy to make mistakes on these. So we have sine of t, comma, cosine of t, comma 3. And then we'll take the integral dt. So recall, dot product, you take your first component with your first component, second component with second component, and third component with third component, and you add them. So our next integral is going to be the integral from 0 to 2 pi. And then we have 3t and negative sine, so it's negative 3t sine t. Then we have cosine and cosine, so plus cosine squared of t. Then we have sine t and 3, so we have plus 3 sine of t dt. Now we can do some quick little simplification and see some stuff happen. So we have negative 3t sine t and then 3 sine t. That doesn't simplify at all. Cosine t doesn't simplify. Okay, so we're just going to distribute our integral across and take some integrals and see what happens. Yeah, that's what we'll do. Cool. So the first one we got is negative 3 integral of t sine t from 0 to 2 pi plus integral of cosine squared of t dt. I should have been writing dt here as well. 0 to 2 pi. And then plus 3 integral of 0 to 2 pi of sine of t dt. Okay, so interestingly here we have a odd function times an odd function, so that's an even function. So this is fine, we'll be able to take that integral, no problem. Now this is an even function, so we're good. Now this is the integral of an odd function. So sometimes these can get interesting. So specifically with sine, if we take this integral, we're going to get cosine, and then we're going to plug in 2 pi minus cosine of 0. So we're going to get 1 and 1, so that's going to be 0. So we can actually go ahead and erase or cross out this last integral. So that one's just going to go to 0. That makes our life a little easier. Interestingly, this one we're going to have to do a little bit of work too before we can figure it out, but I believe it's going to go to 0 as well. We'll get there. Let's take this next one. So we have negative 3. So this t sine t, we're going to have to do integration by parts. So I'm actually going to make myself a little space real quick. We'll do that and we'll leave a little space above so I can rewrite it. There we go. That makes sense. Okay. So integration by parts using the tabular method is usually going to be your best friend here. If you don't know the tabular method, this will be a really fast tutorial on it. I can go more in depth if you have questions about it, but let's just go through it. So you always want to choose your derivative that's going to go to 0 when possible. So in this case, that'll be t. And then the integral will be sine. And this one should work out pretty nicely. Derivative of t is 1, and the derivative of 1 is 0. And the integral of sine is going to be negative cosine. And the integral of negative cosine is negative sine. And then, of course, we go across and diagonal to get our actual integral. So we have t minus t times negative cosine. So we get negative t cosine t. And then we're going to have negative and negative is plus. So we have plus sine t. Right? So that's our integral here for this first part. All of that is multiplied by negative 3. Okay. So our next piece, and of course we're going to evaluate that from 0 to 2 pi. We'll do that here in a minute. So this cosine of 2t could be a little tricky for a lot of people. There's a few ways to deal with this. My favorite personally is just to use trig. So we have identities that deal with cosine of 2t. So I'm actually going to leave that there because we already have it written down, and we're going to work on these identities. So we know that cosine of 2 theta is equal to cosine squared of theta minus sine squared of theta, right? And we know that sine squared of theta plus cosine squared of theta is equal to 1. So let's isolate the sine squared. Since we have cosine squared here, we know we want to be able to plug in cosine squared. So let's isolate the sine squared here so we can plug in a cosine squared, and we'll go from there. So let's take cosine squared over. So we'll get sine squared theta is equal to 1 minus cosine squared of theta. And then we're going to plug that in here. So we get cosine of 2 theta is equal to cosine squared of theta minus 1 cosine squared of theta. Distribute your negative across, and you'll get a negative 1 here and a plus cosine there. Right? And so you have 2 cosine. So we want to isolate cosine. So what we're going to do is we're going to add 1 over and divide by 2. So you get cosine squared of theta is equal to cosine 2 theta plus 1 over 2. And that's our integral, actually. So we're going to integrate this guy from 0 to 2 pi, because we have cosine cosine squared of t, so that works out pretty nicely. And then instead of theta, we have t. Okay? So let's make ourselves some space. Okay, so the integral here, you can distribute your integral across, pull out the 1/2. So we're going to have equals 1/2, the integral from 0 to 2 pi of cosine to t, Jesus, that looks terrible, cosine of 2t, and that's plus the integral from 0 to 2 pi of dt, right? That's dt as well. dt plus, there we go, okay. And that 1/2 is, of course, distributed across both of these since I just pulled it out from here. Okay. This is a pretty straightforward integral on the right, and then this one on the left looks a little complicated, but actually works out really nicely. You just take the integral of the cosine as normal, so we're going to still have our 1/2, and the integral of cosine is just going to be sine, and the inside stays the same, and then you just take the derivative of the inside and divide by that. So the derivative of 2t with respect to t is just 2, so you divide by 2. And then we just have the integral of dt is just t, and that's evaluated from 0 to 2 pi, as well as this. Right? Good. Conveniently for us, we can actually kind of stop there on this one. We don't need to do a whole bunch of expansion, because 2 pi and 0, so you have 4 pi and 0, sine at both of those is 0. So this goes to 0, and now we can just evaluate this last piece, where we get equals 2 pi minus 0, so it's just 2 pi for the t times 1/2. So this piece equals pi. So this one here is going to go to pi. Okay. Oy. All right, let's finish evaluating this one real quick, and then we'll put everything together. So this is our -3 from this first term where we did integration by parts. So we have -3, and then we have -2 pi cosine of 2 pi. And I'm going to actually leave the negative outside of this. Yeah, that'll work. Okay. And then minus 0. And I'm not going to write the rest because 0 times anything is 0. So that's our first piece, and then plus sine of 2 pi minus sine of 0, we already know is going to be 0. So that and that will both be 0. Not my best handwriting, sorry. Negative 3 times negative, this is 0, so we're just dealing with this piece. Cosine of 2 pi goes all the way back around to positive 1. So this is just 1, so that's 2 pi. So we have negative 2 pi here. Negative 3 times negative 2 pi is equal to 6 pi. So this guy goes to 6 pi. And now we can see if we put everything together that our integral here is equal to 6 pi plus 0 equaling 7. Cool, no calculator. Whew. Okay, and that's capacitance. And that actually is pretty good timing because I'm getting tired. But that's everything I wanted to cover. Cool. Well, thanks for joining me. I appreciate it. Really active chat today, which was nice. I will see you guys no later than Wednesday.